Hey everyone, let's tackle problem 2 for the project. I strongly recommend doing problem 1 first, as you get solutions for L1 and L2 which remain the same for part 2. So here, what they're saying is that the solution problem 1 might look smooth, but it doesn't feel smooth because the second derivatives of L1 and F and L2 aren't equal at P and at Q. So we have to insert a couple of cubics in order to fix that. Now just remember, we're calling little f capital F. And they call this new function, this new parabola, it's slightly different. They call it q of x. I don't like this at all, and I don't like that they use a, b, and c because the values are going to be different from what you found in f. So instead what we're going to do is we're going to define a new function, I want it to be a capital letter of sorts, phi of x, capital phi of x, and it's going to equal alpha x squared plus beta x plus gamma. Okay, that will be our new parabola. So now let's see what we're working with. We're still working with L1 and L2 as before. Maybe let's see. Yeah, I'll actually call L2. I guess we'll keep it blue. Keep it blue. All right. Okay. So what we're going to do now, though, is we're going to introduce two new functions, g and h. Now, as before, I want to make them capital. Okay? So g is going to be that. Actually, I really should have phi be in green because that's going to be our new f. Okay? And then h, what should we use for h? I guess we'll make it light blue of sorts. And that's capital. And then, of course, L2 is what it normally was, right? So anyway, we stick a cubic g in between L1 and F, and another cubic h in between F and L2. So we actually have 5 functions, right? So what this gives, let me see if I can graph this in any way that's acceptable. So we still have our line. Well, maybe I'll get my axes out here first. All right, our x and y axes. So we still have point P right here. And we still have our point Q down here or so. Right, and it's still 100 feet away. That has not changed. Nor has L1 changed. That's still a straight line. Slope 0.8. Right, 0.8x. But now we have a cubic g that is pretty close to linear, but it is a little curvy, actually. Then we're going to have the parabola phi, which is going to dip down like this. It goes up and then it goes down. Then we're going to have that cubic q, or sorry, that cubic h touch q. And again, that also, let me try a little bit better. That looks pretty close to a line too, but it actually is a bit curvy. Let me actually make it a little less curvy than that, right? And then we have our line, L2, going down. Okay? So it's actually a very similar looking roller coaster when you graph it all out, but it is slightly different. And in particular, the transitions at P and Q are smoother than they were in the model that we did number 1, because the second derivatives are now able to equal each other at the transition points. So just to be clear, right, here we have L1, here we have G, here we have capital phi, Here we have h, and then last we have L2 as before. Okay. So here we wind up having 11 unknowns, right? K, L, M, N, alpha, beta, gamma, and PQRS. That's 11 unknowns. But fortunately, we have 12 equations that we can use to solve them. So let's write them down, right? Let's do part A. Now, I'm not actually going to write down all 12. I'll write down the first 3. And I'm hoping that you can see the pattern. Notice that what we did in problem 1 was we set the functions and their derivatives equal to each other. But then we said that that wasn't enough. So what we're going to do here is we're going to let the functions and their derivatives and their second derivatives equal each other. So let's see what that gives us. That's going to give us L1 of 0 equals G of 0. All right, actually, maybe I'll just I won't even number them. Well, I will number them. Not that you need to do them in any certain order. You'll be using Mathematica as it turns out, but just to enumerate, I guess. Okay, so that's equation 1. Equation 2 is going to be L1 prime of 0 equals G prime of 0. And then equation 3 is going to be L1 double prime of 0 equals G double prime of 0. Okay? So I will leave it to you to come up with equations 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? They're similar forms. They're using G, Phi, H, and L2, so maybe you see the pattern. I hope you do. Part B requires you to use Mathematica. Okay? I have a video for how to do that. And then part C, which is to graph this and compare it with the plot from 1C, is once again use Desmos. Okay? Just want to reiterate one thing, or just want to iterate one thing if I didn't say it already. Note that L1 of x is still 0.8x. And L2 of x is still negative 1.6x plus 120. And just to be clear, we are solving for this piecewise function. I'll call this script R, fancy script R. This R of x, right, script R of x, which equals, and just to be crystal clear, right, this is going to be 0.8x for x less than or equal to 0. It's going to be g of x, which I guess is what? Kx cubed plus lx squared plus mx plus n for x between 0 and 10. It's going to be capital Phi of x, which is alpha x squared plus beta x plus gamma. I hate to use a different language like Greek letters, but I just want to emphasize that alpha, beta, and gamma are different from A, B, and C. Let's see. Here, x is actually between 10 and 90. Here we're going to have h of x, which is p x cubed plus qx squared plus rx plus s. And that's for x between 90 and 100. And then last but not least, we're going to have L2 of x, which we already know is negative 1.6x. Make that a little bit nicer looking. Oh my gosh. Negative 1.6x plus 120. And that's for x greater than or equal to 100. Okay, so that's what we're solving for. When we get each of these components, then we can graph script R and compare the graph to regular R.